Hi, and welcome to this talk, Large-Scale CFD Simulations on AWS. My name is Neil Ashton. I'm a Principal CFD Specialist. And what I wanted to talk about was how I feel that moving to the cloud can really help you to break away from the constraints of your HPC environment and can give yourself or your end users the ability to focus on design and getting CFD simulations done and not worrying about the infrastructure behind it. I also want to touch on why I think that CFD in general is going to be used more and why we need to move to higher fidelity methods to reduce the need to use wind tunnels and physical testing, which ultimately I think will allow you to move at a quicker pace towards new designs. So let's jump into that then. So what's the motivation for CFD? What's the bigger picture reasons for this? Well, the whole of the automotive, the aerospace, the engineering sector is going through a lot of change. Most are moving to electric vehicles. Many are moving to autonomous vehicles. And this drives big changes, big changes. If you look at a car, whereas it used to be the idea of a very standard car, passengers sat at the front facing forward, which drives essentially the shape of the car. If you now move to an electric autonomous, you can come up with designs like you see here, which are radically different. And from a CFD and an aerodynamics point of view, that means that you probably can't use the knowledge you had before because these shapes are just so different. Now, of course, how you could do it is you could, be building these sort of things and testing them physically on the road or in the air. Now, whilst that is ultimately the source of truth, it is the real thing, it is expensive to build a car or a plane or really anything. And that's because it's not just about the external shape, which is what a lot of the time CFD or aerodynamicists think about, or even doing heat transfer. It's you have to have the safety test, you have to have an engine, you have to have all the rest of the thing ready, where often at the early stages, all you want to know is my design going to give me more range in my battery or reduce the heat or something? So whilst they have a place, we really want to reduce the need for these physical tests as much as possible. This is especially true, of course, once you get into the air, just because the cost and the safety side just gets so much bigger. Now, of course, it's true to say that we already don't have to rely on on physical testing. Sorry, we can also go into wind tunnels, and then we have a mock-up of it. Now, that is certainly less expensive than doing the real thing in the air or on a road, but it is considerably still more expensive than the methods that I'll speak in a moment, because you have to still make this model. You have to take it to some sort of facility. Now, if you're a large company who have invested in wind tunnels, you already have probably one in your factory, and maybe therefore it's not so expensive for you to do it. However, if you're a startup and you don't have access to your own wind tunnel, then actually there is quite a significant cost and time delay to doing these tests. So again, they have their place, but really, if we want to be moving as quickly as possible through the design process, we want to limit any of these blockers that potentially take time and money. And of course, again, in the aerospace side, there is additional technical challenges like the ability of the wind tunnel to match the environment, which means we have to go to very specialist tunnels like the one shown here that are cryogenic tunnels just to achieve the conditions. If not, you have to go to these, I often show this slide in presentations, these massive wind tunnels. In the bottom right of the picture, probably you can't see it on your screen, there's a tiny car. This tunnel is immense. It's at NASA Ames. And whilst it is a great tunnel and is used by many companies, it's obvious that this is quite expensive and quite a specialist facility. And there's some things that simply won't fit it anywhere. I like to give this example of the Bloodhound project, a car trying to go 1,000 miles an hour. There's very few facilities in the world that could cope with a car that has wheels and is going supersonic. It just doesn't really exist. So obviously this is where the CFD comes into, the dream of no manufacturing. It's cheap and fast. And the question, of course, is it accurate? Now, cheap and fast is what we'll discuss today, essentially. So we could, of course, do DNS, which is the most accurate form of CFD. In this sense, no assumptions are made, no modeling is made. We simply solve these Navier-Stokes equations using some code of our choice. And if we do it with a sufficient number of grid points, with a certain accuracy of the schemes and time steps, we can get ourselves a pretty close representation of the actual physical flow field. The problem for this is, and I've done some kind of back of the envelope calculations here, that we would need maybe for a car around 10 billion cells, probably therefore to have an appropriate CFL number, we'd have to have a time step of 1 e to the minus 7 approximately. Now, if you work out, we'd have to do 4 seconds of flow to go over the car. That probably gives us about 40 million iterations. Now, it's very hard because it depends on the code, but just going off some ideas of the seconds per time step based upon a certain number of cells per core, I'd come out with about 200,000 cores for 92 days. Now, that is possible, but what I thought would be interesting to do would be, well, what would be the price of that? So actually, if you were to assume, 3 cents per core hour, and it doesn't matter really whether it's double that or it's half that, because it still comes out in the tens of millions. And so the key point here is that whilst it is possible to do a very accurate CFD simulation, we always have to consider what's the cost of the simulation as well, or whether that would actually be suitable. So in this case, my argument is that the DNS is simply not possible because in an engineering environment at the moment, because even if we could do it, it would be simply too expensive. You could build a wind tunnel for $13 million, or certainly you could after 5 runs, let's say. So you could go to an LES. This is where we start to add some modeling in, and we start to reduce, therefore, the grid dependency, because we can start to model some of the smaller scales. But you still need, low billions of cells, still 1 e to the minus 6, which, using the same logic, would come out to about 40,000 cores for about 12 days. So hundreds of thousands of dollars. This is starting to get into the territory of used in research programs where we really need to have this data because maybe we can't do physical testing. Think of nuclear reactors or inside very complicated bits of geometry. But it's still probably too expensive to be routinely used. And again, let's compare the cost against physical testing. Would it just not be cheaper to go to a wind tunnel, let's say? So this is where we get to RANDs, Reynolds Average Navier-Stokes. And this is what most people are using now. This is considerably cheaper because typically it's steady state. You need far less computational grid. So we're now talking maybe just 2,500 cores for maybe 2 hours. And the key point here is the cost, maybe around $100. The sum, much less, some a bit more, but the order of magnitude is really what gives it here. The problem is that we know that RAND is not accurate enough for many things, which means that people have to use wind tunnels. Now, what's recently come around more and more is this hybrid RAND LES, this idea of saying, well, let's use RAND where it's good and use LES where it's not. And by combining them, we can also lower the computational cost. So now if we were to still take the academic guidelines, we're talking maybe 20,000 cores for hundreds of hours. So rather than being $300,000, maybe 60,000. Now this is still quite expensive, but you get a lot of accuracy. And we'll comment in a moment about ways to reduce that cost even further. But just for a moment, here's a few data points to prove why we feel there's a need for this high fidelity CFD. And this just is something actually that's a few years old now, but I think actually represents the point quite well. In that this study was looking at some various cars using CFD and comparing against experiments. And essentially what it shows is that certain car shapes, so fastback, actually don't do too bad. The lift and drag is reasonably well predicted. But if you move to an estate-like vehicle, which is more like an SUV type as well, then whilst the drag may be not so bad, the lift is really poorly predicted. And this basically means that if you don't move to these hybrid RANs, you wouldn't really know what the lift was going to be. And this has impact on stability and things like that. Now, of course, $60,000 that I showed per run would probably be too expensive for industry. And so actually, there's always assumptions that are made. So people use larger time steps, people make coarser grids. But still, even if you were to do that, you would probably need about 500 cores for about 4 days. And here we come now into the turnaround time. For engineers to use these high fidelity methods, they need to be available in a similar time frame that RANDS is. So waiting 4 days for a simulation is probably too long. So we therefore need ideally more cores to scale the problem out so we can get it less than a day. But I mean, how many people have access to over 2,000 cores for every single job? And if you were to decide right now to do it, would you have the capacity? And this is where the HPC bottleneck comes in, and I believe where the cloud starts to help. So for me, the classic HPC issues from my background before I was working at AWS was always, I'm stuck in a queue. I need to get my job run, and can you bump up my priority, please? Why is this user always hogging the queue? Or I've run out of disk space. Please, can I have a terabyte more? I promise I'll move some files. And I'm kind of half joking here, but that actually does mean that you're spending time sorting these things out rather than running your case. If you do want to run a big case, how many times have you realized that there's no space on the cluster? I'd have to wait a week for it to get started. And then what if something goes wrong? So all that means that you're less likely to do it, and you're more likely to give HPC resources as a reason that you can't do it. And so for me, this is really where the cloud angle comes in, because I believe that most companies will phase in the use of high fidelity alongside their standard. So they need steady capacity for their kind of typical workload, but they need the ability to burst maybe to higher cores for these sort of hybrid RANs or more LES, or even move to GPUs. And my simple point is cloud HPC can do both. It can give you the steady state capacity, and it can give you the ability to burst more. And it also gives you the ability to do it wherever you want to do it. So if you're a large company, you don't have to have a single huge cluster and you tell people from all around the world to log into that cluster. In fact, you can actually have several clusters, which are maybe individually smaller, but could be better suited to the people who need it. So if you've got engineers or people in the US, they can have their own cluster. People in Europe can have their own, people in Asia. So you can really split out this idea of some massive single cluster. I don't believe needs to exist anymore. So how is AWS doing these things? Well, one, it has huge capacity and a large infrastructure. It has a wide choice of architectures, the CPU and GPU options for any type of code that you want to run, CPU or GPU based, whether memory is different. There is, modern high performance file systems so that you can have hundreds of terabytes of storage when you need it just for your need. And you can do all the customization that you want for it. But of course, one key thing is how you orchestrate it, how you create it. And this is where I think the parallel cluster really comes in handy. So instead of you having to manually do this, which of course you could do, we have a tool that I will show you later in a demo, can actually create this cluster in a matter of minutes. You can specify how much storage, the compute, and we'll go off and create it for you. Now, of course, the other good thing, talking about this burst versus steady state, is we have different cost models. So you can have a reserved instance savings plan model where you pay either upfront or partially or even not upfront, but you have a committed spend that basically means that you can get really significant discounts by saying, I know I'm going to need 100 nodes, so I might as well go for these models, but whilst also having the ability to burst with on-demand and spot pricing models. So this means you can combine all of them. You don't have to only be thinking in a burst-like on-demand fashion. You can also get significant cost savings by actually having reserved instances and savings plans for those known steady state workloads. So that goes back to my comment that really the cloud and HPC is not just for burst, it can be for everything. Now, I wanted to bring out one key point about GPUs, because most CFD codes that are being used by industry right now are CPU based. But we are on the edge, I believe, of a large-scale movement towards GPUs. It's been a long time coming, but I really feel as if we're getting there now. And this work really illustrates it for me. It's something we did with Zenatech, a company down in Bristol, where they're doing a simulation of 150 million cells for an aircraft simulation. And the graph shows the performance an on-premise CPU, which is in yellow. Then we have our C5N, which we'll go into a moment, Intel instances, Amazon EC2 instances, which is the light blue. And you can see it's faster than the on-prem. That's nice to see. But the real big things is the GPUs. So even when you scale out the CPUs to, I think in this case, over 3,000 cores, they're kind of reaching the limit of scaling. This is a RANS simulation using a finite volume type code. And it's when you go to the GPUs, and particularly I point out to the P4D, so the NVIDIA A100, so the red line, where you see a 2 to 3 times speed up. That's really significant because the CPU was already at the edge of scaling. It couldn't really get much faster. And what most people would assume is that this is great, but it'd be more expensive. But you'd be wrong because it's actually cheaper. There's so much compute power in those GPUs that for this code, you can actually go 2 to 3 times faster for 2 to 3 times cheaper. And here's the key thing with the cloud. If you want to change your whole cluster to a GPU-based cluster, you can do it. It's just a line of code. You don't have to completely change everything. And I think that's a really key one. And if you want to experiment with GPUs, you don't need to go off and buy some. You can just actually test it in your cloud environment. So I've given all these things, but how about some actual examples of companies that are doing it before we get into the demo? Well, one of the companies that really needed to move to these high fidelity CFD was Formula One. Formula One management wanted to design the 2022 rules, and they didn't have access to wind tunnels for 1 to 2 years or very limited usage. And before AWS, jobs were taking more than 60 hours on, and they only had a couple of hundred cores they could run on. By moving to AWS, they were able to reduce that from 60 to more like 10 or 12 hours because they could run on thousands of cores for every single job. And they used Amazon EC2 C5N. So these are 36 core, 192 gig Intel Skylake instances with our Elastic Fabric adapter to give the really high network bandwidth and low latency. And they use parallel cluster to provision this all. And as Pat Simmer said, this was one of the revolutionary projects in the history of Formula One aerodynamics, the whole project. And I think AWS at least gave them the thing that they didn't have to worry about the HPC bit. They could focus on the design. And this is true also for Ineos, the America's Cup team. We helped them when they were needing to go through tens of thousands of designs, which would have taken 20 times longer on-prem. They just simply didn't have the capacity. We were able to do this even with our spot cost, which is 70 to 90% lower than on demand. And we were able to give them, again, the ability to focus on design rather than the HPC environment. Now, one of the examples I really like is also with Joby. So Joby Aviation are designing a novel aircraft to really revolutionize personal mobility. So, an eVTOL. And what was key here, which goes back to my argument of CFD and wind tunnels, is this is a novel aircraft. It didn't have lots of prior experience. And they were in a startup in an innovative area wanting just to get designs. They didn't want to be slowed down by physical testing. So by moving to AWS, they were able to conduct thousands of simulations on hundreds of cores using parallel cluster and the EC2 instance that I mentioned about. And the nice point here was that they also use S3 Glacier to store the hundreds of terabytes of data. So they never need to get rid of anything just in case they need it in the future. And as Alex said here, basically using AWS enables them to get stuff faster, which maybe have taken a week, they can do in less than 24 hours. And my final example is Boom. So, supersonic, who doesn't want to see supersonic aircraft again? What a fantastic thing Concorde was. And they've gone all in on AWS for exactly the same reason. Using simulation, using CFD helps them to do things faster. And moving to AWS and having this in a cloud environment means they just don't need to worry about provisioning things up front. They can just use resources as they need. Now, what I wanted to show today was an actual demo so that you can see it's not just all talk, that you can actually see it in action. And the one thing I'm going to show is a simulation that I was doing for this automotive CFD prediction workshop. It's an international community effort to bring people together to look at improving CFD methods to answer that accuracy question. So in this case, I was using SimCenter STAR-CCM by Siemens. This is a fastback variant, so it looks like a saloon type car. For the CFD people here, you can read the details of the simulation. But it was a reasonably large simulation, several hundred million cells. What made it big was the time step. It was a very small time step, so I had to do lots and lots of iterations. And the reality is, if I had run this only on 300 and something cores, it would have taken about 15 days to do all these simulations, which was just frankly too long because we needed the results in for the workshop and we needed to actually look at what was going on. So instead, by using AWS, which of course I did because I work for AWS, was that I can use Amazon EC2 C5N instances and go from 360 cores to 14,000 cores and get that back now in 9 hours or 12 hours, basically less than a day. which is a considerable speed up. And basically what you see is the code actually scales really nicely, about 20,000 cells per core, and it's still scaling. So this is a really good example. And as I said, what I'm going to do now is I will actually show you that case running so you can actually get a feel of how we provisioned the cluster, which is what we'll do now.
Okay, so what I wanted to do was to guide you through the process that I would go through to create the cluster, to install the code and run the simulation that I just showed, of a large-scale, high-fidelity CFD simulation. So I'm going to be using Parallel Cluster. That's a tool that we create that essentially means you can create a cluster just by a line of code. And that's where we'll start today. So if you follow the workshop that I'll show at the end of this presentation, that basically has everything that I'm going through. In general, it has the sort of step-by-step to go right from a fresh account to creating a cluster and running the type of job that I am today. So once you've installed Parallel Cluster, that literally takes a few lines, and I won't show it here just for the sake of time, you can start to build out your configuration file. And I've got an example one here that I'm going to use, which probably isn't going to be too different than what you could use. So basically, you give it some things to create the cluster. So you say where you want it. We have 25 regions, so I'm going to tell it to run in Ireland today, so EUS1. I could change it to run in the other AWS regions just by changing the region name. Then further down, I have things like the operating system, whether it be Amazon Linux 2, whether it be CentOS, for example. We have the scheduler, so whether it be Slurm or Torque. I'm using Slurm here. We then have the master instance type, so the head node. This depends on what you need it to do. If you're going to have quite a few users, quite a few people, you might have a larger instance. So M5N24X large is a higher memory, so 384 gigabyte Intel Cascade Lake instance with 48 cores. I picked that just because it has the highest network bandwidth, and it's an example of a larger instance, which would be the example if you had quite a few people using the system. And then when you go to queue settings, you can set up multiple queues so that your users could have different ones for meshing, for solving, and I'll discuss in a moment the solve burst, and then post-processing, for example. I then give it access to my S3 buckets. In this, I have a very open access. Normally, people would restrict it. And then we have FSX for Lustre settings. And so here, what I wanted to show you was, imagine, my scenario here is imagine you're a reasonably large user of CFD with quite a need for storage. And so what I'm going to do here is I'm creating a 240 terabyte file system, persistent, which basically means that it has some data replication going on to give you more redundancy. And what I also like is, well, this is with SSD. This has a 50 megabits per second per terabyte throughput. I could change that to be higher, but I actually just don't need it in this example. It's more just of an example. And what I like is the automatic backup. So every single day, it's going to back up the file system. So it's really nice because it means that, one, if you had some issue, you could restart from it. If a user said they deleted something by mistake, but also that backup can be transferred to different regions. So if I wanted to replicate this cluster in a different region, I personally find it's a very simple way. I could have all my data move across and just start again. So then what we've got is the settings. And by the way, this is just an example. If you want to deep dive into FSX for Lustre, there's some really great videos out there and blogs, so I definitely encourage you to do it. This is more of a CFD focused thing rather than the details of each of the underlying services that we're going to use. Then we have the queuing here. So we have basically different queues. So I'm saying I need a mesh queue. And what that means for me is that I've got one instance, M5, which has 380 gigs of RAM. Got an R5 that have 700. Now we could go higher, but this is just an example of people who don't need lots of nodes, but they just need high memory nodes. And we can give it certain things like the cost model, on demand, spot, etc. Placement groups as it brings them closer together to improve performance. And one of the things, though, that you'll see here, now, normally, well, quite often, people would like to use parallel cluster in AWS for the ability for it to scale up only when it's needed. So the example would be, if I set that minimum count to 0, when I create this cluster, it's going to create the head node, so an M5N, and it's going to create the storage, but it won't create any compute nodes. It has a minimum count of 0. But when I submit a job that I'll show later, then it will spin up to the desired amount, up to the maximum in this case, which is just a user-defined thing. What I'm doing is just out of interest to show that you can have this, what I'm saying, steady state, which is you can actually have a more traditional looking HPC cluster by setting the minimum count to be what you want. So in this case, I'm setting it to 10, which basically means 10 nodes will come up when I create this cluster, and they will stay up. And you can't create more than 10 nodes. So if a user submits more than 10, or rather, you have 10 users who all submit 2, then some of them will start queuing because you've set the limit. But this is at your control. And the reason I've done this is I've assumed that maybe you want it to be as close to your on-prem as possible, and you'd like to maybe take advantage of reserved instances or savings plans to have essentially you pay for that and you get heavily discounted either upfront or not upfront, or even partially upfront. So this is kind of the cloud replicating an on-prem style system where you have a fixed number of nodes and they come up and they're always up. And I'll do that for different ones, and I'll have, just so I show here, a solve queue. So I'll have one with 300 nodes, so it's just over 10,000 cores. They'll come up and they'll stay up. But I'll also have what I'm calling here a kind of a burst. So this is a separate queue that could go beyond those 300 nodes if you needed to. So this arbitrarily I'll set as 50, but it could be whatever number you want it to be. And then finally, I'll have a post, so I'll have some GPUs for people who want to run the GPUs. And so with all of that, basically what I can then do is create the cluster. So I do pcluster create, and maybe I'll give it a name, so maybe CFD Demo, and I'll press enter. Now, this will take anywhere from 5 to 10 or maybe 20 minutes, depending on the size of the file system and things like that. So we'll come back to this once it's finished, and then you'll see how it's been created, and we can get in and install the code and run a case. Okay, so we can see it's been created now. So by my reckoning, I think it was about 22, and it's 48 now. So yeah, about 26 minutes. Now I think this is a little bit longer because it is quite a large file system, over 200 terabytes. And we're provisioning the capacity. We did the minimum to already be 300, so it's actually already done that. So if you're not doing those and it's just creating a head node and a small file system, about 5 to 10 minutes. So what we can do now, as you can see, it's created this cluster. We can actually just SSH to it. So the name was demo, and we just use the key that was provisioned. Say yes, and now we're on to the cluster. Now, this is your cluster, so it can be defined exactly as you want it. There are a few things that come with it, so, OpenMPI, Intel MPI. Depending on when you're watching this, there may already be a later version, and so some of the things that I'm showing here, there may be now updated versions. But essentially what you're seeing is, if you're compiling your code or running your code, you already have the various MPI flavors there, but there are no codes. Now, if I do a df-h, so you can see the file systems, you can see that I've got this /fsx, which is, over 200 terabytes that took about 20 minutes to create. Now, if I do sinfo, you can see the queues that I have, and you can see the nodes that are up. So I've got my 20 nodes for the mesh, 10 for the post, 300 for the solve, and 50 for the burst. But you see the idle with the tilde, so you can see they're not actually there yet, but if we need them, they will be there. So what we're going to do is we're going to now go and install the code and then start running a case. Okay, so I've actually gone ahead and installed STAR-CCM just to make it a bit quicker. I'm using STAR-CCM in this case, but obviously the same process would work for other codes. I also went and downloaded the case, but if you just want to see how I would do it, I would just simply download it from one of the buckets, S3 buckets that I have, and I can just transfer it here like this. This is a reasonably large file, so it did take a bit of time, and there are ways to optimize the transfer uploads and downloads to S3. I haven't done that, so we're just seeing the plain 250 or something megabytes a second, but it is possible to get considerably more than that if you spend some time optimizing it. So I'll just cancel that because I already actually have the file, so I don't need to do that. And what I will do simply is to show you the sort of submission script. So it's pretty simple. It's like anything else that you'd probably see on Slurm, where I say the number of tasks. So in this case, I'll just use the whole cluster. So it's just over 10,000 cores. My partition was solve. You remember that links to what I created in the parallel cluster, and my constraint is the instance type. So obviously, if I wanted to run the mesh queue, I just put mesh here and pick the M5 or the R5. STAR-CCM already has the Slurm integration with it, and I'm not using any special flags. I'm using Intel MPI, and I just specify it. So that's it. I haven't done anything particularly fancy. Hopefully that looks similar to people who run STAR-CCM. This could be replaced by a Fluent or an OpenFOAM, or name your CFD code. So what I can do, if I just type SQ, you can see there's nothing running. I can do sinfo again. So what I'll do is I'm going to submit the case. This submit's different because it has my license key in, so that's why I have two different files, but it is the same submission script. And what happens now is it's running straight away because I've already made the nodes. So they're already there, and therefore I don't need to wait. I don't need to queue. They just run straight away. That's the model that I was talking about, that if you wanted to have them, you can do, which is kind of like an on-prem model where they're already there. So that was the example that I wanted to show you. So if we wait a moment, then the job will start, and then we can see how it's running. So there we can see the job running. You can see it's about 0.18. Well, if you do some quick maths on your calculator, 200,000 iterations times that, you get to about 9 hours. So this is going to run on. It's obviously a bit of an example run. Then it'll save the file, and then you could copy it back to S3 or run. Now, obviously, I've got a huge file system of over 200 terabytes, which is massively overkill. But the demonstration was really that we could be running a job. Now, let's cancel this, and let's try and run now one of the burst jobs. Let's go beyond the nodes that I've already provisioned, and you can see how they come up. So I'll close out here, and then I've created another script that's my burst one that's going to submit to 50 nodes. So I'll put my thing in the queue, and so now it's not running straight away because it actually has to go and provision it. So we'll wait a few minutes. It usually takes about 2 to 3 minutes, and then those 50 nodes will come up, and that job will run. So these are the two different models. With the 50 node example, you're not paying for it until it actually comes up. So this is your kind of on-demand burst, and many customers actually only use this model. They never want to just have idle capacity. They want to only have the job come up and down just as they need it, which is the most agile way. But I wanted to show the other way, so you could see, you can do both. You can have the kind of steady state, and you can have the one that's just coming up and coming down. So let's just wait for that to come up, and then you'll see it running. Okay, we can see this job is also running, obviously running much more slowly, but you can see how that job came up now on 1800 cores. Of course, these are arbitrary numbers that I picked on the 300 nodes, 50 nodes. It could be the other way around, could be many more. It's completely what you need. The principle is you've been able to create a cluster in the short amount of time, run your job, and either do it in a purely on-demand way, purely elastic way, or you can upfront provision and this links to our different costing models. Okay, so now we could actually just copy the file back up to S3 if we wanted to finish that simulation and store it for another time. And then copy it on. Again, you can optimize the speed of the S3 transfer through various mechanisms. What I'm doing here is just without any optimizations whatsoever. But you can see the ease you can move the file back up to S3, and then I can also move the file around between different regions if I wanted to move my cluster around, etc. So hopefully this has been an example of where I've shown how you can create a cluster. Obviously this is the bare bones. You could add multi-user, LDAP, Active Directory, however you want. You can customize it to exactly your needs. But you've seen how you can create a cluster in around 20 minutes or so. Tens of thousands of cores, hundreds of terabytes, and you just install your code and run it, and you can completely customize it to your need. So I hope that's been useful, just as a quick visualization rather than just purely slides. And I hope you'll take the time to actually try it for yourself.
Okay, well, hopefully you enjoyed that talk and you enjoyed that demo. Simply, I'm saying that I think large-scale high-fidelity CFD is needed to reduce the reliance on wind tunnel and physical testing, and hopefully given some of the background on that and give you some customer examples. I think that HPC is actually a key bottleneck to achieve RANs like turnaround time. And I think the cloud model can help broaden HPC access. I think this is really important also for startups, who just need to focus on innovation of product and not about, provisioning and buying on-prem resources. And of course, as I showed, you can spin up tens of thousands of cores, hundreds of terabytes of HPC systems in just a matter of minutes. And I think the key thing here is that you can change the configuration with just a line of code. If GPU code comes around, you can change it to GPUs. So the key thing is engineers are not blocked by a lack of HPC resources. They can get on with what they need to do. And if you would like to have a go at doing this, there's a workshop here, which is on our website. You can follow that link there, which is basically a step-by-step guide of exactly what I just did, how you create a cluster, how you'd install a code and run it. With that, I'd like to thank you for listening in, and I hope to speak and see to some of you soon. Thank you very much.